Okay, let's take a look at a little summary of what we find in chapter 2. And here, the concept of the transfer function is defined as a relationship uh, between an output of the system, which is right here, and the input of the system, which is over here. Okay, and in this case, what we want is some relationship between this output and the input. In fact, what we have said is that the transfer function is the output in the S domain in relationship to the input, right? But what about if you have other systems in between? We still want the relationship between this output and the relationship between this input right here. Okay, so let's take a look at. In summary, you have a, a function of the Laplace transform that we can relate to for different functions. Although for the purposes of the transfer function, the most important one is the integration and the differentiation. The fact that we have that the S operator is d dt like this, and we define it 1 over s as the integral of the function dt. D of whatever you could say, let's call it function, whatever function is, and then this function here. These are the two most important because you got to remember. Here we have, on your book, makes a table of all these transformations that you will find, but it's not as important as those two that I told you. A transfer function has a, like I said, going a little deeper into the subject. The idea here is that you have a, sorry, you have a relation, a ratio between the the output and the input, and that comes usually in terms of in sense like on a fraction here, where this is the numerator. The numerator is over here is the numerator, and this is the denominator. Yeah. So if you look in detail as to what we have done on the equations of each one of the elements that make up a system, you will see that in here you have a capacitor, and the voltage is 1 over C times the integral of dt. Or you could write the equation the other way in terms of the current. Okay, and in terms of the Laplace transform, this is what you will see. All right. For the resistor, voltage is R times I, or I is 1 over R times voltage, and so you have in here the Laplace operator on that, and this would be for the inductor. So this is the kind of thing that we have done so far on how we obtain the bond graph models of this, or the equations, or we have seen it in the previous lectures. So just to reiterate, when you do a bond graph model of this, as we would like to do several examples of this, we put the one junction for the current, then we attach the elements, you see, like this, to that current, and this is the I element, and this is the source of effort, you see. This is the bond graph model, what you see on the in red, the model of this particular circuit. Let's give it a try. We will have the transfer function, once we put it into the CAMG software, will come out in this form for this. But the purpose of this explanation is, what about if you have one of these? And what about if you have one that has three of them? That's what I am concerned about. So in here you have, you put the one junction for each one of the currents like this, I1, and this is I sub 2. And then you put this C element over here, the R element over there. This again is the R element over here. This would be the source of effort on the side. And in between these two, you have this current minus this other one, and that is going to be your I element. And that's the end of this one. What about if we increase it now for something like this? Okay, let's take a look in here. You do the same thing. You have three of them in here. So this is I1 and I sub 2, again a 1, and this I sub 3. Let's keep doing this. This, you have the C element. I'm going to go a little farther up. This would be the R element over here. This is going to be your source of effort on the side. And in between these two, you have a 1 with the R element in here. And in between these two, you have a 1 with the I there. And that's the end of that. So this way, we will continue doing more examples, a little more complex. Okay.